Alright, so in using the method of initial rates to find a reaction's order, what you do is you'll get a set of data like this. Remember, zero order, the rate doesn't change no matter the concentration. So you'd be looking at data like this. As we doubled the concentration, the rate stayed the same. Doubled it again, the rate stayed the same. So no change took place. For first order, notice that as we double the concentration, we doubled the rate. We double it again, we doubled it again. And then second order, you double the concentration, you quadruple. Double again, quadruple again. And so this is what you're going to be doing. You'll be looking at initial rates in concentration and see how the change in concentration affects the rate. And if you notice the pattern, then you know pretty easily. If you don't notice the pattern, then you're going to have to do something like this. So you'll take one rate divided by the other, and you just set up the rate law. You actually take the rate law of one divided by the rate law of the other, and the rate constants are going to cancel because it's the same reaction. You'll get a number here for the rate divided by the rate, and then this right here you can actually set up to be A, the concentration of A at time 2, or at concentration 2, A, concentration 1, and then raise that to the n. So then you'll get a number here, and then all you have to do is solve for the order. So in this case, you have 0.24 divided by 0.06. This is the very last example that was second order a couple slides back. So basically 24 divided by 6 is 4, and then the k's cancel. 4 divided by 2 is 2 raised to the n, and then you're like, oh, okay, 2 raised to what is 4 is 2. You get the second order. Okay, so if you have more than one reactant, this becomes the rate law, all right? And it's the same thing, you're just adding on another reactant. And now the rate, or the order, rather, of the entire reaction is m plus n, right? It's not just m or n. So with any reaction, you can have the order with respect to one thing, or you can have the overall order of the reaction. So in this case, the overall order is m plus n, but the order of the reaction with respect to A is m, and the order of the reaction with respect to B is n. So there's a couple different ways to word it, and you got to be careful about that. So in this case, you have first order with respect to hydrogen, first order with respect to iodine, and then second order overall. And that's really all there is to it there. Here, this is a practice problem that I think would be good to go over. So write the rate law. Well, the rate law requires us to find the orders. So first of all, there's two reactants. So the rate will be equal to K times the concentration of NO2 raised to something times the concentration of carbon monoxide raised to something. Well, to find the order for each individual reactant, take it one at a time. So let's focus on the first one. Nitrogen dioxide, notice that we double the concentration here. That's what we want, but we have to find 2 points where we hold the carbon monoxide constant. We want to know how nitrogen dioxide is affecting the rate, not how nitrogen monoxide is, because we're focusing on this. So because these are held constant, that means it didn't matter. So when we doubled the concentration of nitrogen dioxide, notice the rate quadrupled. Multiply by 4. Now, this is more realistic data because it's not perfect. Okay, 0.0084 would have been perfect, but it's not. So we're looking at second order with respect to nitrogen dioxide. And then, oops, I gotta go like this, so 2 there. Now we want to focus on carbon monoxide. So we want to find 2 points that stay the same with nitrogen dioxide so that they don't matter. And then as we doubled the concentration, notice that nothing happened. Now you're like, oh yeah, something did happen, it got a little bit faster. Well, not enough to matter. So that means that this is 0 order. So that means that it's second order with respect to nitrogen dioxide, 0 order with respect to carbon monoxide, and second order overall. Now how do we find the rate constant? All you got to do is plug and chug. So usually I'll use the last point because I haven't used it yet. So the rate is 0.033. We're going to solve for k, plug in 0.40 here, and then, not that it matters, but we can plug in 0.10 there, and then just solve for k. That's all you got to do. All right, I think that's a good place to stop for now.